Okay, in this video we're going to take a look at a couple of examples of drawing FPDs, and we're also going to be doing a whole lot more of FPD drawing in class so that you have plenty of practice. So what I have here is I've already drawn for you the first FPD that I would like for you to draw, and to help you understand what you're looking at, you have a wall or immovable surface on the left, and that is denoted by these slash marks along that line. And then up top here we just have an immovable surface, which could be the ceiling or some type of bar. And from that bar we have a sign which is hanging from two cables. And so I want you to answer these questions and draw an FBD, and then I'm going to come back and we're going to work on it together. Okay, welcome back. And the first thing we're going to do is answer these questions before we start to draw our FBD. The first thing we want to know is the sign in equilibrium or non-equilibrium. And this is going to be equilibrium. How do we know that it's equilibrium? Because it's not accelerating. It's not changing speed or direction. The next question to successfully draw this FBD is we need to know how many touches do we have. And our object of focus here is going to be the sign. So how many touches do we have? We have two separate cables. So that's going to be 2. How many contact forces can exist? Now for this one, you need to be careful, because if you go back to your force catalog, you're going to see that a string can only ever exert a single force on the object. Now you need to be careful here, because if you go back to your force catalog, you're going to see that a string can only ever exert a single force on an object, unlike a hard flat surface like the tabletop, which is capable of producing up to 2 different forces. But for strings, it's only one force, and that's the tension force. So how many contact forces can exist? That's going to be 2. Now, how many forces do exist? How many total forces exist? Or I should say, how many contact forces actually do exist? And the number of contact forces is equal to 2. The total number of forces that's going to be equal to 3. And that's because we always have the one non-contact force, which is gravity. So to draw our FBD, we draw a box, and then we take note of the contact, and this happens to be a string. The force is always going to be pointing away from my object and parallel to the string, so that's going to be up and to the right. So we'll call this FT1. You could have called it FT right if you wanted to. Then we have another touch which will be parallel to the string. That's going to be FT2. And then we have one non-contact force which is pointing straight down. And that's going to be the force of gravity. Now, when we draw a head-to-tail diagram of these forces, we should end up with no resultant to the diagram. If we take our forces and just bring them out and draw an HTT, and it doesn't matter what order you add them in, you might start with the force of gravity pointing straight down. Then we have FT1 points up and to the right. And that should actually be a little longer. All right, and then we have FT2 points up and to the left. And you can see that we're back to where we started. And so this FBD does show us equilibrium. Now the important thing to remember when you're doing this, if you're going to be using the head-to-tail diagram, is that your forces are going to have to be drawn approximately to scale so that you have a sense of what's going on. If you don't draw these arrows approximately to the right lengths, then this head to tail diagram is never going to work for you. Let's go on to our next question. Okay, in this example, we have a block which is at rest on a rough ramp. And that's all you know. The block is at rest on a rough ramp. Your task now is to draw an FBD. Please go ahead and answer these questions. And where it says how many contact forces do exist, also list out for your next question how many total forces exist. Okay, welcome back. And the first thing we're going to see here is that this block, it tells us that it's at rest. So this is going to be equilibrium. How many touches do we have? Be careful here. There's only one touch. That's the touch of the ramp and the block. Those are the two surfaces coming into contact. So there's one touch. Now, how many contact forces can exist? For every touch that's not from a string or from a fluid, for every touch, up to 2 forces can exist. So that's going to be 2, because it's 2 times one surface, one set of surfaces. So that's going to be 2. How many contact forces do exist? The normal force, which will always exist whenever you have a touch, and then we have the force of friction. Now, friction, remember, it's a reactionary force, so it exists when another force exists parallel to it. Okay, so it's, in this case, we have our non-contact force of gravity, which is pointing straight down. But gravity has 2 components, one which is perpendicular to the ramp, and the other which is parallel to the ramp. And so the friction force is opposing. Now this is not a real force, that's why I'm not putting it on my FBD, that's why I'm using a dotted line here. But the gravitational force is attempting to pull the box down the ramp, so friction is going to point up the ramp. So how many contact forces do exist? We have 2. How many total forces exist? That's going to be the number of contact plus the non-contact, which is 2 plus 1 for gravity, which is equal to 3. So our FBD is going to be the normal force, the force of gravity, and then the force of friction, which is parallel to the ramp. Okay, now I want to emphasize something here, and I cannot emphasize this enough, and that is that when you draw a free body diagram, you never include force components on your diagram. So that would be FG parallel and FG perpendicular. You never include these on a free body diagram, especially on the AP exam. If you include FG parallel or FG perpendicular on the AP exam, you're going to end up losing points. And those are easy points. You never want to give up the easy ones. If there's a hard question, yeah, that's understandable that you might lose a point. But these are free points whenever they exist on the exam, so you don't ever want to mess that up. So our free body diagram should have a total of 3 forces, and that's what we have. If you drew a diagram that looked like this, where you have the normal force, FG parallel, FG perpendicular, that would be friction. Force of friction, and then FG perpendicular. If you did that, then this would be incorrect. This is not a free body diagram. Okay, so we'll talk about these more later, but you don't want to be doing these in the space designated for free body diagrams. All right, now if we want to double check to make sure that we've drawn this correctly, we can draw a head to tail diagram. So we have the normal force points up and to the right. We have the force of gravity, which points straight down. and then we have the friction force, which points up and to the left. So you could see that we come into that vicinity. We're only sketching this head to tail diagram. We're not drawing it precisely. And as a result, I didn't quite end up where I should, but we're approximately at 0, and this is approximately a 90-degree angle here. And so I can have some measure of confidence that the block really is at rest. Now, if by chance you didn't include friction, that's where this is going to be helpful. If for some reason you didn't include friction, so let's erase friction from our diagram. If you didn't include friction and you drew a head-to-tail diagram for that, then what you would have is the normal force points up and to the right, the force of gravity points straight down, and then you have this big empty space in here. And that indicates that there is a resultant vector. And the resultant vector always goes from where you started to where you ended. Okay, and so the fact that you have that resultant vectors means that you're in non-equilibrium. So this diagram indicates non-equilibrium. And if that were the situation, that tells you that you did something wrong. So here, even though it's not exactly perfect, it tells us that we're in the ballpark. We've probably included everything we needed to. Here, we're nowhere in the ballpark in the vicinity of being back to our starting point. That indicates non-equilibrium, which means we're missing something, or you've done something grossly incorrect.